playlist reservations in two-way slabs by means of yield lines, and we will deal with case 4, and this will be as follows. You have a rectangular slab with a size A and B, simply supported on all sides. It's a two-way slab. It means that this dimension is between A and 2A. Then we make a reservation in the slab, but case 4 is a centric hole, which is a hole in the center of the slab, which is attracting the yield lines. So we are not using the yield lines of the slab without the hole, because when this hole is centric, it's most likely that the yield lines or that the hole will attract the yield lines. So this means that from this corner where the two rotation axes crosses, it will go directly to the corner of the reservation. The conditions are, because it's centric, of course, that D4 this side is equal to D4 that side. That's the horizontal symmetry, and the same thing in the vertical symmetry. So that are the conditions. Of course, the hole is smaller than the size of the slab. So these are the conditions. And to visualize it, you can have a hole like that, perfectly in the middle, or like that, perfectly in the middle, or like that, or like this. So now you have an idea what we call centric hole attracting yield lines, case 4. We will now calculate the work done by the external forces. Then you will see that this side is about 2 triangles in the 4 corners. So you have, for triangles, it's delta over 3. So the mean deflection of that slab is 1/3 of the maximum, and it's d3 times d4. d3 times d4. So around this hole, the deflection is delta. So that's why this is now d3 times d4, which is this surface times q divided by, multiplied by delta over 3, which gives you this. And it's 4 times. There in each corner, it's 4 times. Because it's symmetric, so that makes the formulas a little bit easier. And then you add up the square or rectangular sections, which is of course d3 times d2 twice, and d4 times d1 twice, which is this. And you divide it by 2 because the mean deflection is delta divided by 2 for a rectangular element. The virtual work done by the internal bending moments is then equal to, this is the yield line projected to the north. It gives you this line, means d4, and the angle is theta divided by d3. So you got this d4 divided by d3, and you got it 4 times in the 4 corners. And then in the other direction, in the x direction, you have the yield line projected to the rotation axis, give you d3, and the angle is delta divided by d4. So you got 4 times because of the 4 corners. So that's the bending moment. We know now that d4 is a function of d1 and d2 because it's a centric hole. Now we lose 2 parameters by that. And this is the bending moment of a centric hole attracting the yield lines. When I say that, you must be very careful, because if d3 gets very small, it's not realistic to suppose that the yield line is going this q. So you must be careful when you use this, that you still need a mechanism that the different slab elements can rotate about. Now let's make it without dimensions, and we know already what the bearing capacity definition is. It's the maximum bending moment without the hole divided by the maximum bending moment with the hole. Without the hole, this is the maximum bending moment. And the bearing capacity is then using this non-dimensional parameters equal to this formula. Now, when you examine this formula, you see immediately when this means that B can never be equal to D2 because, or D2 can never be equal to B because then the formula gets infinity. So you cannot use this formula for B equals to D2. The same happens for A equals D1. It's not possible. So the hole cannot be over the total width or the total length of the slab. So this is just to illustrate if D2 is equal to B, then you have a hole like that. And otherwise, this condition is a hole like that. So those are the extremes of the bearing capacity formula. We can make a graph on the y-axis of the bearing capacity, on the x-axis, the ratio of length and width of the slab. Now you see that sometimes it's above 100%, sometimes below. But most of the time it's below. So in a centric hole, you lose bearing capacity because it's most of the time below 100%. We can now take one particular point, for instance, the red curve. Alpha is, for instance, 1.6 here, 1.6. And alpha 1 is 0.2, and alpha 2 is also 0.2, which is the size of the hole, centric. This point is 95. You see, okay, this corresponds. So it's 95%. A small hole like that of 20% of the size of the smallest size of the slab reduces your bearing capacity of the slab. Now we can take another point, the green curve, for instance. You see now you have a rectangular. It loses 12% of the bearing capacity. Or a third point, this one, it gives you almost 18% of the bearing capacity for this type of hole. Now let's look at a square hole in a square slab, centric. Then you can fill in the different parameters and you obtain this nice formula. We calculate the bearing capacity in function of alpha 1, which is the size, in fact, is the size of the reservation. Alpha 1 is in fact D1 divided by A. Then you get this formula. You can put it in a graph. Y-axis is the bearing capacity, x-axis is the size of the square hole. And now we find something very, very interesting. This curve goes down the 100%. So in this region, you lose bearing capacity. In the other region, no worry. The bearing capacity is more than without the hole. And you see this point, 0.5. And this point is 0.25. So the bearing capacity is 100% when the hole is equal to half the dimension of the slab. When it's bigger, then no problem. You can do that. It's no problem. But if it's smaller, you have to be careful. And the maximum, and when it's alpha 1, 0, of course, then you have 100%, which is the capacity of the flap without the hole. And you see here, the maximum is like 11%. So when you make a hole, a centric hole in a square slab, and the dimension of the hole is 1/4 of the size of the slab, then you reach a loss in bearing capacity of 11%. So this is indicated by this zone. So this is the dangerous zone, in fact. So making a reservation in a square slab in the center, be careful, stay out of this zone. So to conclude, it is the graph with this zone, a square hole with a size of half the length or width of the slab in a square isolated slab leads to a loss in bearing capacity with a maximum of 11% at a hole size of 1/4 of the length of the slab, which is that point.